Lifting properties are going to be extremely important in our future work, and so I want to start right off the bat by defining them, and I'll try to build an intuition as we go. It's just good in my opinion to know the general definition first. So yeah, we have a category and a class of morphisms C in that category. Then we have a map P, which implicitly also contains the information about the spaces E in its domain, B its codomain. And P is said to have the right lifting property against morphisms in C if every commuting square admits a lift in the following way. So this diagram commutes. We will equivalently and more often say that P is a C-injective morphism when this is the case. So there's a little bit to be careful about here. A lift needs to exist only if a commuting square exists. Let's try to see how this can be useful with regards to homotopy. Suppose we are trying to understand the nth homotopy group of a topological space B. This is the set of homotopy equivalence classes of maps from Sn to B, but this might be quite untractable or hard to calculate. But what if we could just study a part of the entire set of homotopy equivalence classes? Well, we could find a space E and a map from E to B such that the following diagram commutes. But since we are interested in homotopy equivalence classes of maps, we should probably require that if maps from Sn to B are homotopic, then so are their lifts. Then, in a sense, we have a situation where the amount pi n of E differs from pi n of B is measured by the map from E to B. We can also rearrange this idea into a way that lets us see the the connection to the right lifting property from before. This general pattern where the bottom left object is a standard cylinder object of the top left object is called a homotopy lifting property. In the case where we replace Sn with some random topological space X, we see that the map from E to B is a Hurewicz fibration. The other notable case is when we replace Sn with Dn, and that is what we turn to now. So yeah, a Serre fibration is a J-tope injective morphism, i.e. a map that has the right lifting property against the class of generating acyclic cofibrations. Remember that we are trying to generalize topological homotopy theory. What we will show eventually is that the specific shape of dn in dn times I doesn't matter with respect to the properties of the Serre fibration that we are looking for. What really matters is that these maps that the Serre fibrations lift against are relative cell complexes and weak homotopy equivalences, which I think is pretty neat. Again, we will cover that later once we develop abstract homotopy theory. So going back to our goal of generality, many of the statements we are going to give in the rest of the video have analogous statements in a more general setting. Presently, we defer the proof of this statement to the next video or the video after that, where we will prove it in generality. But in this case, it says that a Serre fibration not only has the right lifting property against J-tope, which is the definition, but also against all retracts of J-tope relative cell complexes, which is a pretty considerable extension if you think about it, and it's really neat that it works out like that in my opinion. Here's a cool proposition that we are ready to prove. We'll actually return to this and prove a more general version of it later, like I was saying before, but for now, suppose F is a Serre fibration and that Y is any point in Y. Then we can consider the fiber of Y, which we'll call Fy, as a subset of X, and hence we have the following fiber inclusion. This proposition states that on the level of homotopy groups, the induced sequence is exact. So let's prove this. The sequence is exact just means that the kernel of the second map is the image of the first, so immediately we see that one direction is clear. Suppose you are a sphere and hence a representative of an equivalence class of the homotopy group in Fy. Well, by definition you are mapped to a single point Y under F asterisk, since you are in the fiber over that single point Y, i.e. in Fy. So what we are left to show is that this is the entire kernel, the other direction, i.e. that every sphere in X that maps trivially into Y is homotopic to a sphere that is entirely contained in Fy. So to get formal, let alpha be something in the kernel. So it is a map from a sphere to X. Our goal is to show that alpha is homotopic to something in the image of the inclusion. So it is homotopic to a sphere that is sent entirely to a single point in Y. As far as proof techniques go, one of our assumptions was that F was a Serre fibration, so we better arrange our diagram in a way that lets us exploit this fact. So we can think of alpha, or indeed any map from the sphere, as fitting into this diagram. So what we are doing is sort of packaging the information of F compose alpha into some map kappa. So by assumption, alpha composed with F is trivial, and hence it, and by analogy kappa, is left homotopic to the constant map sending everything to a single point y. That's what it means to be trivial. Well, again, as soon as you hear homotopy, technically left homotopy, you should think of what it means for the diagram. In this case, it means that our square becomes something like this. We can rewrite this diagram in this way, so we can exploit some patterns. In particular, consider the top two squares. Again, we'd like to exploit the fact that F is a Serre vibration, but as of right now, we can construct any lifts because the left morphism in the square is not a generating acyclic cofibration. But recall by the previous proposition that said Serre vibrations also lift against J-tope relative cell complexes. Well, recall that the inclusion of a CW complex, such as a sphere, into its cylinder object is a J-tope relative cell complex. So you should be thinking, how can we squeeze in an Sn-1 times I into this top part? Well, the two top right morphisms are F and identity. The identity is sort of redundant. So what if we deleted that middle row containing dn, kappa, and y? We could then replace the dn with Sn-1 times I and rearrange the top two squares in the following way. Great. Now we can use the fact that F is a Serre vibration and obtain a lift at eta tilde. What is this homotopy between? Well, it is between the top map alpha and some other map alpha prime. We can imagine alpha as living on the top of the cylinder Sn-1 times I, and alpha prime living on the bottom of that cylinder. So I just want to reaffirm that this is what we want. We wanted to say something about all maps homotopic to an element alpha in the kernel. In particular, we wanted to say that alpha was homotopic to a map that is trivial, i.e. sends everything to a single point. This such map lives in the image, and would show that the kernel and image are isomorphic. So let's show that this map alpha prime could be a constant map. We again piece together all of our information that we have accumulated into the following diagram, which finally exhibits what we want, since the outer square commutes and alpha prime is the top two morphisms. Looking back at what we did, we used the fact that kappa was homotopic to the constant map to construct a homotopy eta, and then show that we could lift it in a suitable way against eta. Here's our last lemma for this section, and fair warning, this is a bit of a larger effort to prove. The lemma comes from something you might have been wondering. Like sure, Serre vibrations lift against generating acyclic cofibrations, but what about just regular generating cofibrations? It turns out that the maps that lift against I-tope, the generating cofibrations, are precisely the acyclic Serre vibrations, i.e. Serre vibrations that are also weak homotopy equivalences. So we have this nifty sort of duality, where acyclic Serre vibrations are those maps that lift against regular generating cofibrations, and regular Serre vibrations are those that lift against acyclic generating cofibrations. So the forward direction is not so bad to prove. So we're starting with an I-tope injective morphism, and we want to show that it is first of all a weak homotopy equivalence, and secondly that it is a Serre vibration, which will show that it is an acyclic Serre vibration. So by assumption there exists a lift. To show that it is a weak homotopy equivalence, we want to show that all homotopy groups/sets are isomorphic. You might see why this should be true, because in the top left we have maps out of Sn, which define the homotopy groups. But okay, when n is 0, dn is d0, which is just a point, and its boundary, or S-1, is just the empty set. Well, the bottom map, which is a map with domain a single point, just defines a point in X, and if every such map lifts, then we automatically get that P is surjective, since we can always lift to a point in X that maps X hat that maps to X under P. If n equals 1, we see that 2 points being connected in X means there is a map from D1, which is isomorphic to I, with each point as the endpoint of its image, so kind of like a path connecting them. Well, that I connects them in a sense, and again we can lift the whole map from I to x hat. So we get a connected component in x hat whose endpoints correspond to those 2 points in x. So we get a component in x hat, a connected component in x hat corresponding to the connected component in x. So P is injective on the level of connected homotopy groups, and this is paired with the aforementioned surjectivity, shows that P is an isomorphism on the level of the zeroth homotopy set. So for n greater than or equal to 1, suppose you were a trivial element in the nth homotopy group of X. Since you are a map from Sn to X, and you are trivial, that means you can be factored through Dn plus 1 via a map that sends its boundary to a trivial thing in X. This makes sense because a map from Dn plus 1 is contractible and hence trivial. So if you could be factored through it, you had to be trivial in the first place. Well, then there is a lifting from Dn plus 1 to x hat, which again tells us that this map from Sn to Dn plus 1 up to x hat, which is equivalently the top map, is trivial. What does this tell us? Well, on the level of nth homotopy groups, if you were trivial in pi n of x, then your preimage under P was trivial in pi n of x hat, which means the kernel of P is trivial, and hence P is injective on the level of nth homotopy groups. It remains only to show that P is surjective. To see this, consider an element of pi n of x. Well, another way of saying that other than as a map from Sn is as a map from Dn that sends the boundary to a single point. In other words, this diagram here. Well, there is a lift by assumption, so there is a corresponding representative of that element in pi n of x in pi n of x hat, and we are done with showing that P is a weak homotopy equivalence. To show that it is a Serre fibration is not that hard. We recall the previous fact from last video that every element of J-tope is an I-tope relative cell complex. Something we will prove in the next few videos is that by closure this implies that I-tope injective morphisms lift against I-tope relative cell complexes. So in this case they lift against, in particular, elements of J-tope, which shows that it is indeed a Serre fibration. As a bit of forewarning, the proof of the reverse direction which we turn to now is a significantly greater effort than the forward direction. If you follow along, however, I think you will find it to be very elegant and insightful. I'll do my best to make sense of it. So our assumption here is that we are starting with an acyclic Serre fibration F, and we need to show that this lifts against a set of generating cofibrations. These are the inclusions of the boundary into the n-sphere. Like above, the fact that F is acyclic and hence a weak homotopy equivalence means that F is surjective, and so there exists a lift in the n equals 0 case and in the n equals 1 case, which is again just formulating that connected components are images of connected components. Again, this is just from the proof of the forward direction. The interesting things happen for n greater than or equal to 2. We want to show that we can construct lifts for commuting squares of this form. Since alpha compose F factors through a map kappa from the n-disk, this shows that the image of alpha under F is trivial in the n-1 homotopy group of y at little y. So little y and little x are just the image of the chosen base point in Sn-1. Well, since F is an isomorphism on the level of homotopy groups, by assumption, alpha itself is trivial in the n-1 homotopy group of x at little x. So since it's trivial, we can do the same thing and observe that alpha being trivial is equivalent to the existence of a map kappa prime, such that this upper triangle commutes. So far so good, but the real issue and our focus for the remainder of the proof is that the bottom triangle doesn't necessarily commute. Our goal will be to show that we can find a map rho prime interchangeable with kappa prime, such that both the upper and lower triangles commute. A little bit of rearranging gives us this commuting square. Now you look at this square and realize you actually know the push out of the square. It's an elementary example we covered before. It's the n-sphere. Hence we can use the universal property of pushouts to obtain a unique map kappa comma f composed with kappa prime. So as a bit of warning on the notation, the maps kappa and f compose kappa prime in the square are actually from Dn to y, but we write it in this way to express the universal property succinctly. Also, this pair parentheses notation for the maps from Sn to y has components which reflect the fact that it is induced via the universal property of pushouts with respect to the maps or cocone with maps kappa and F composed with kappa prime. Well, okay, this is nice. We have that this unique map is by definition a representative of the nth homotopy group of Y and Y. Well, again, since F is an isomorphism on the level of homotopy groups, this corresponds to the image of an equivalence class of some other map rho from Sn to X. Immediately we observe that this is the bottom triangle from the original square. We had that the top triangle commuted and wanted to show that the bottom one did too. But that one had diagonal map as kappa prime, so we want to rewrite rho with that in mind. So again, we remember that Sn is a pushout. To do anything with that, we need two maps from Dn to X, over which we can use the universal property to obtain some unique map out of Sn. So we can imagine that one of these maps carries the information of kappa prime and the other of kappa. Kappa prime is actually a map from Dn to X, so we can use that. Regular kappa isn't, however, so we can just use a placeholder, rho prime, to keep track of this information. This exhibits the map rho is of the form rho prime comma kappa prime. Okay, so we have something of this form. Why did we do this? Well, the idea is that rho prime is a suitable substitute for kappa prime, when the bottom map is just kappa. Well, here's something cool about this new pushout map defined here. It is in fact trivial. So for the first line, we recall that kappa prime was defined to be such that F composed kappa prime was kappa. So in the first line, the first summand is just that substitution. And the second is a trivial element, i.e. in the class from kappa to itself. For the second line, we just factor out F from the first summand. For the third line, we observe that F of rho prime kappa prime from the second line was just kappa comma F composed kappa prime from the commuting bottom triangle we just saw. And from this it is clear that this is 0. Well, okay, so because we can just include Sn into the standard interval object of Dn, we already had a homotopy from kappa to F composed rho prime, which we can call phi. So phi is just the extension of the previous map F composed rho prime comma kappa to the cylinder object over Dn. Well, phi is that map on the boundary of the cylinder object. So what does that mean? It means that the map is constant on the boundary of Dn. Why? Well, consider each Dn to be a hemisphere of Sn, so they are attached along their boundaries to form Sn. Then since the map out of Sn attached along their boundaries, since the map out of Sn is trivial and can be mapped to a single point, this means we could squash the hemispheres together, as this is also trivial homotopy type. If it was a circle, this would amount to having opposite points in the circle and holding them still while deforming the two hemispheres so that hemisphere lines so that they're identified. But okay, phi is constant on the boundary. Why is this important? Well, consider the situation we have, i.e. what phi is saying. It's saying right now that this diagram sort of commutes, almost commutes, i.e. it seems to commute up to homotopy, but we want it to literally commute. But what does phi actually tell us? Since it's constant on the boundary, it can be considered as a map out of Sn minus 1 union Dn times I, attached along the cylinder Sn minus 1 times I. Intuitively, this means that each moment of the homotopy, which is a cross-section of Dn times I, the boundary is unchanged, which is just saying that the map is fixed on the boundary. But wow, this is just asking to be put in a pushout diagram. But what maps are we doing the pushout over? Well, certainly it contains the information of phi, but remember that we had that commuting square. We wanted the image of phi to agree with alpha compose F. We want everything to commute after all, and alpha is really the only thing that we haven't accounted for yet. We'll see this in a bit. So previously our diagram with phi didn't reflect the fact that it fixed the boundary, and this new map just reflects that fact. But what's the nice thing about this attaching space? It's homeomorphic to Dn times I again. So we can rewrite the homotopy phi between kappa and rho prime compose F with this new map F compose alpha comma phi. And finally we can use the observation that F is a Serre fibration to demonstrate the following lift. And looking back at our square, this is precisely showing that the map's kappa is rho prime composed with F by commutativity, which shows that the bottom triangle commutes as desired. Furthermore, the fact that alpha is in the middle map ensures that the entire square commutes. So hopefully you found that proof to be pretty neat. For now, that's all I have. We've in fact finished the first section of the nLab, topological homotopy theory. Starting next time, we'll get into the real substance of the theory, abstract homotopy theory.